In this video, we're going to be discussing roots of systems and a new tool for analyzing um, dynamic systems known as the root locus. So we're going to start by thinking about the exponential function, e to the pt. So we've seen the exponential function. Here, I'm going to rewrite this. It's e to the p times t. There we go. Um, we've seen the exponential function a lot. It comes up in solutions to linear second order systems. So if we have x double dot plus 2 zeta omega n x dot plus omega n squared x equals 0, then in previous videos we've used the method of assumed solutions to solve for this thing to find that x equals c1 e to the p1 times t plus c2 times e to the p2 times t. And so we're really interested in this exponential function e to the pt, particularly when we're talking about these exponential functions. We're interested in those values for p1 and p2, which we call the roots of the system. We call them the roots because if we write the characteristic equation, which comes from the method of assumed solutions, I'll refer you back to that video. So the characteristic equation for the equation that we've written up at the top is p squared plus 2 zeta omega n p plus omega n squared. So you'll notice it's the same coefficients that are in front of the dependent variable x and its derivatives, but instead of x and its derivatives, we have p and p squared, and this equals 0 when we're going through that method of assumed solution. So this is what's known as the characteristic equation of a system. And the values of p that make this equation true, that make that expression equal to 0, are known as the roots of the system. So p1, p2 are roots. And we can use these roots to understand what the system looks like. So if we're looking at e to the pt, if p is positive, we get exponential growth. Um, if p is negative, we get, instead of exponential growth, we get exponential decay. Um, and if we're getting exponential growth, if a system is growing off to infinity because its roots are positive, we call that unstable. Um, and if p is less than 0 but not 0, then the system is stable. P can be a complex number, so we use so what we can do is plot P on the real complex plane. So if we've got real components of P here and imaginary components of P on that vertical axis, then any poles in what we call here the left half plane, if any individual single pole of a system is over there, then on the left, or I'm sorry, on the right, I know left and right, on the right half plane, those are unstable systems. That's an unstable system. If any pole has a positive real component. On the other hand, this half, I'll go ahead and shade in the right half plane is right here, anywhere there. If you're in the left half plane, if all poles are in the left half plane, then the system is stable and it's going to eventually converge to a steady state value. So it's stable if all the poles are in the left half plane. If you have any poles that are on that imaginary axis, so if P equals plus or minus some constant times I, then that system is neutrally stable. There is no exponential growth or exponential decay. It's just going to oscillate forever around it's going to oscillate around some constant value forever. So we call that neutrally stable. Because we're dealing with e to the pt, you can see that p is a multiplier by t. So if the absolute value of p is large, then you have a large value multiplied by t. That leads to a fast response. So the system either decays to zero very quickly or explodes to infinity very quickly. And if the absolute value of your pole is small, it's a slow response. So if you have time and you're multiplying it by a tenth, then it's going to take you 10 times as long to get wherever the system is going. So I'll draw here a fast response is going to look either like this or like this, where it decays very quickly. That's a fast response. And over here, a slow response is the opposite. It's either going to exponentially grow much slower, or it's going to have exponential decay that is much slower. Oops, not like that. Where'd my they'll still pass through the the same initial condition. We'll draw the initial condition up here, but it's going to be slow. A slow decay that eventually makes it to zero. So we'll go ahead and take a break there and continue in the next video.